The Porsche 992 GT3 RS is one of the most talked about performance cars of the modern era. Not because it dominates on horsepower, and not because it chases top speed records, but because it represents something genuinely rare in road car engineering. A production vehicle designed around aerodynamics as the primary performance system. And to appreciate what Porsche has done here, you need to understand one idea up front. Downforce is not created by pushing air down. The most effective downforce is created by pressure differentials, regions of low pressure that pull the car toward the road, and high pressure management that prevents lift from developing in the first place. That's why the numbers on this car are so extreme. Porsche quotes 409 kilograms of downforce at 200 kilometers per hour and 860 kilograms at 285 kilometers per hour, effectively approaching the mass of the car itself, pushing it into the asphalt at speed. They also state that this is double the downforce of the previous 991.2 GT3 RS and multiple times that of the standard GT3. In other words, this isn't an aero package, it's an aero platform, and the result isn't theoretical. Porsche recorded an official Nürburgring Nordschleife lap time of 6 minutes 49 seconds and 328 milliseconds on the 20.8 kilometers configuration, over 10 seconds quicker than the 992 GT3 in their published comparison. This is one of those rare cases where aero is not just a talking point, it's the reason the car exists. So in this video, we're going to break down the GT3 RS the way an engineer would, starting with the biggest, most visually dominant aerodynamic feature, then tracing how Porsche conditions the flow upstream, protects the underbody, and even designs the cooling system as part of the pressure field. Let's begin. If you had to pick one component that defines the new GT3 RS, it's the rear wing. But what makes this wing special isn't just its size. It's the fact that Porsche treated it like a motorsport device, designed to operate near its aerodynamic limits while remaining stable across yaw, braking, and speed changes. This is a multi-element wing, which means it's not just one airfoil. It's multiple lifting surfaces working together with a controlled slot gap between elements. That slot gap is not aesthetic. It's a mechanism for boundary layer management. It's so effective that even the MR variant of the GT3 RS exhibits the same design for the rear wing, just with an increase in overall aggressiveness. Here's the aerodynamic problem a wing always faces as you increase angle of attack. You increase the pressure difference, higher pressure above and lower pressure below, and that produces downforce. But as that pressure gradient becomes more aggressive, the flow on the suction side has to work harder to stay attached. The boundary layer, the slow-moving region near the surface, can lose momentum, separate, and cause the wing to stall, generating a sudden downforce loss and drag spike. Multi-element wings delay stall by keeping the suction side flow energized. The slot gap allows higher energy air to pass through and re-energize the region downstream, effectively resetting the boundary layer. This allows the wing to run higher effective camber and higher lift coefficient without separating. This is why multi-element wings are a staple in racing. They generate large downforce while preserving operating range and stability. Then there's DRS, which in this car is not just a straight-line gimmick. At high downforce, induced drag becomes a major penalty because strong downforce correlates with strong vertical structures and pressure losses. DRS reduces the effective surface area of the wing and weakens those induced effects, reducing drag on straights. But the deeper point is balance management. The rear wing is such a dominant downforce contributor that being able to adjust it dynamically allows the car to maintain a usable aero balance across different phases of a lap. And the wing is mounted with Swan-Neck supports, which matters more than most people realize. The underside of a downforce wing, its suction surface, is extremely sensitive to disturbance. Traditional mounts under the wing create local separation and disrupt the low pressure region you're paying for. Swan-Neck mounting supports the wing from above, leaving the suction surface cleaner and improving lift-to-drag efficiency. It's a direct motorsport solution applied to a road car. On the MR variant, you'll also see a shark fin element. That fin isn't there to make downforce directly. It's there for yaw stability, to guide airflow toward the rear wing when the car is operating at slip angle. At yaw, the wing sees asymmetric inflow, and sections of the wing can experience earlier separation. A fin helps keep the wing fed with more coherent flow, improving consistency in high-speed cornering where stability matters more than peak numbers. Moving forward from the wing, the roof devices can look small, almost decorative, but they serve a very real aerodynamic purpose. As air flows over the roof, friction slows the flow near the surface, and the boundary layer thickens as it travels downstream. The thicker it becomes, the more prone it is to separation, especially as the roof curvature transitions toward the rear of the car. Separation upstream of the wing is catastrophic for performance because the wing doesn't just need air, it needs high quality in flow. Attached, coherent, and energetic enough to withstand the pressure gradients of a high downforce wing. The roof strakes and Vortex generators deliberately create controlled vortices, and the important phrasing here is controlled. These vortices are not random turbulence, they're organized, rotating structures, with low pressure cores that effectively pull higher energy air from above the surface down, redistributing the momentum on the surface and re-energizing the boundary layer, delaying separation. It's not that they add energy to the air, they change the momentum distribution so that the near-wall flow doesn't run out of momentum before it reaches the wing. That's race car thinking. Similar to the rear wing, a more extreme set of Vortex generators providing the same effects can be found on the MR variant of the GT3 RS. Now we get to the core of the GT3 RS. The rear wing is the signature, but the underbody is where a huge fraction of the efficient downforce is produced, and where Porsche's systems engineering shows up most clearly. A flat floor and diffuser work by generating downforce through pressure reduction beneath the car. In simplified terms, accelerate the flow under the vehicle, lower the static pressure, and the pressure difference between the upper surfaces and the underbody pulls the car down. But the underbody is also the most sensitive aerodynamic system on the car. Its performance depends heavily on ride height, pitch, and most critically, flow quality. If turbulent, high-energy wheel wake contaminates the underfloor region, the low-pressure structure breaks down and you lose efficiency. That's why the GT3 RS doesn't just have a floor, it has an entire system dedicated to conditioning and protecting the flow beneath the car. The splitter is the first major piece of that system. It is not just a front lip, it is the leading edge boundary condition that establishes the pressure field for everything downstream. The splitter creates a high-pressure stagnation region above it, while encouraging accelerated lower pressure flow below. That pressure differential strengthens underbody suction and sets up the flow path that feeds the floor and diffuser. Then come the wheels, arguably the greatest aerodynamic threat on any road car. Rotating wheels generate strong vortices, unsteady separation, and turbulent wakes. If that turbulence spills under the car, it increases mixing, raises effective underbody pressure, and reduces the coherent low-pressure region the floor is trying to maintain. This is where the GT3 RS gets very motorsport-like. It uses Vortex generators and flow control elements behind the front wheels. Their purpose is to create organized vertical structures that run along the floor edges. These structures act like virtual skirts, forming a shear layer barrier between the low-pressure underfloor region and the higher-pressure chaotic flow outside. It's not a perfect seal, but it significantly reduces lateral inflow and preserves underbody pressure integrity. At the rear, the diffuser performs controlled pressure recovery. As underfloor flow exits, the diffuser expands the flow passage, reducing velocity and recovering pressure. That recovery is essential. It's what allows the low-pressure region under the floor to remain stable upstream. But the diffuser is limited by separation. Expand the flow too aggressively, and the boundary layer cannot remain attached. The diffuser stalls, downforce collapses, and drag and instability rise. This is why strakes matter. Strakes guide the flow, manage vortex structures, and limit lateral mixing across the diffuser. Porsche's diffuser strake design, often including curvature and careful channeling, is about stability, keeping the diffuser effective across more operating conditions, particularly when rear wheel wake tries to interfere with diffuser expansion. The MR variant once again displays the same design philosophy, just more extreme. Now, one last system people often forget is cooling, and on the GT3 RS, it belongs in an aero discussion because cooling flow is driven by pressure, and pressure is what makes the car work. cooling air is never free. Any air you ingest and exhaust changes the pressure field around the car, alters drag, and can create lift if managed poorly. At speed, the front of the car is a high-pressure stagnation region. If you trap that pressure under the hood, you're effectively building a lift device. If you vent it intelligently, you reduce lift, and you also control where that air goes so it doesn't destabilize the underbody. That's why the hood venting matters. It's pressure relief first, cooling second. It prevents pressure buildup under the bonnet and helps keep the front axle planted, while also providing a controlled exit path for radiator flow. The same thinking applies at the wheels. Wheel housings are pressure traps. Rotating wheels pump air and build pressure, and that pressure increases drag and interferes with nearby aero devices. Wheelhouse venting and extraction reduces that trapped pressure, improving the quality of the side flow and reducing weight chaos that would otherwise contaminate the downstream aero. And finally, brake cooling. Brake ducts must deliver mass flow, but the exit flow matters just as much. Hot air leaving the wheel region interacts with the wheel wake. If it's dumped badly, it increases mixing, drag, and can pollute the underfloor and diffuser region. The goal here is controlled extraction that cools the brakes while minimizing aerodynamic penalties. And that's exactly what Porsche was able to accomplish with the 992 GT3 RS. The Porsche 992 GT3 RS is not defined by any single component. Its performance comes from integration. A rear wing designed like a racing device fed by conditioned roof flow. An underbody system protected from wheel wake by Vortex sealing strategies, and cooling systems designed as part of the pressure architecture rather than holes that let air in and out. That is why this car is so fast in the real world. Not just in perfect CFD conditions, but on a real track, at yaw, underbraking, over bumps, and through long high-speed cornering where stability matters more than peak values. It's not just an aerodynamic car, it's an aerodynamic system. If you found this breakdown useful, consider liking the video and subscribing for more engineering-driven analysis. Thanks for watching.